As you know, Elad is out of town today, so I'm the TA for this class, Pierluigi, for those who are watching the video and are not always at the discussion sessions. And so, yeah, I'm happy to walk you through the end, let's say, of last lecture about common mode feedback, and then we start multi-stage amplifiers today. I mean, it's a topic that you may know about from your undergrad, right, already a lot, but we will see it under a different perspective and with some advanced topics as well. So, but first of all, okay, let's catch up where we were, like where you were actually about capacitive common mode feedback. I think Elad told you why we actually like this topology, right? And we want to use also capacitive sensing for this feedback configuration and for this common mode feedback configuration. That's precisely the same reason why we use capacitive feedback also in switched capacitor circuits and normally in integrated circuits, right? So it's not loading too much the amplifier. Here we have, we are assuming that we have a telescopic topology, but you can use whatever amplifier you can imagine of. And it's nice because capacitors don't load too much, right? The differential path. And plus, basically, okay, they really fits the switched capacitor paradigm. So actually, just to clarify, we will assume, of course, that there is some bias in circuits somewhere, and so we draw our bias in circuit. It's my first time with a tablet, so if basically the drawings are funky, just forgive me. And so as we were saying, so we are assuming that at DC, right, we have some current mirror here that is providing maybe with some resistor the biasing that we want. And that resistor is just there because we want to make sure that, okay, we just transfer the DC and the common mode is coupled with the correct node, the gate of the tail current mirror, right? Basically, as much as possible at any possible frequency. So we also like this scheme, as maybe Elad mentioned last time, because actually we are deciding to just control one place, right? Only one spot, only the tail current there, not only the two different current mirrors that are, or let's say current sources that are on the top, just because having only one spot to control is better than having two, just because otherwise there is some conversion from common mode. There might be some conversion from common mode to differential mode due to the fact that there might be some mismatches in the two paths that you control. Maybe you saw this last time. But anyway, so the idea, okay, this topology is also pretty easy, right, to implement, simple to do. The point here is how do we size? Now do we choose CCM, right? So basically, that's one of the design trade-off that we have here. So what's your idea about that? So there are some hints already in the slides. So one would say, okay, let's go for just small CCM, right? But what does this imply? So the common mode loop gain could be low. So can anybody tell me? Let's try to sketch and to compute actually here the common mode loop gain, right? So let's break the loop and assume, for instance, that you have some signal here, right? So how much is the gain from the, let's say, V bias, which is actually the sense gain, right? We could call it the sense gain, from V bias to V common mode out. So how much is this transfer function? If you can consider this node as a V common mode out, or also there is also some common mode here, right? Any guess about that? To this V bias net. So it's a capacitive divider, right? Basically, we are breaking the loop. That's open loop, the common mode loop gain. So it's basically, if you consider that here you have common mode and here also you have common mode, it's basically 2 times CCM, right? Divided by 2 times CCM plus CGS. So if you make it very small, if you make the CCM very small, then you might have a common mode loop gain low just because the sense, let's say, amplification could be small, right? So the sensing system. But okay, is that what worries us most? Let's see. On the other side, okay, you could go with the, let's say, as big as possible CCM, and then you would have, okay, very good sensing gain, right, as close as 1. But then indeed your loading then becomes large. Now, yeah, you have a question?
So the two come from the fact that you're sort of looking at the voltage in the middle of the
right. Yeah, because we have basically two, let's say, entrance point, two entry point for the common mode. So you can imagine it to tie up. So let's say only this path would be CCM over CGS plus CCM, if you can only consider that one. So the idea here is you anyway, as maybe Lad mentioned already, you may anyway need some cap, right, for noise purposes at the output. And so you may want to use this cap as a CCM, basically also to sense your common mode. But certainly you don't want much more cap than you need, right, for noise, or because this is just DC biasing, and you don't want to spend a lot of power just to have a good DC bias point, right, because it's not really power that you are using efficiently for settling or for your bandwidth. So if this is the sense gain, but anyway, as you noticed, we're not even using an amplifier in this loop. So is this enough, right? So that's our question right now. Well, actually, my claim is kind of enough in most of the times, because indeed, as you see, even if the sense gain is at most could be 1, right, for very huge CCM, but what happens then? What is the path? So if you really go and write the full expression, let's say, of the loop gain, right, for the common mode. So what do you have is, okay, for sure this component, A sense. But then, so we are here now at the gate of the tail device. So basically we have for sure the GM, right, of the tail. And then, okay, you can imagine you have some current here, and whatever the arrow at this point of the differential path is, then you can get it as an open loop gain, right, in the common mode path. So is that clear? So I'm driving this transistor. So I get the GM for the common mode, and then some arrow there. Okay, so you can pretty easily express this as a function of the differential gain right now. You just need to basically normalize or divide and multiply by the GM of the differential pair, right? So you still can get this A sense time, basically if I multiply and divide by the GM of the input device. So I have GMRO, which is then the amplification, the gain of the differential mode, times the GM of the tail device divided by GM1, basically GM of the input device, right? So now you are pretty expert in translating GM relations into V star relations. So we could even get a little different expression for this just by using the V stars of the transistor. And so this is basically this expression, this ratio between the two GMs is basically twice the V star of the input device divided by the V tail. Just the factor of 2 is motivated by the fact that the tail current is actually splits for the common mode into 2, right, at bias point. So the current that flows into the input device, it's 1/2 of the current that flows into the tail device. So there is this factor of 2 in the V stars. So the whole message here and the whole point here is that even if you go with A sense equal to 1, right, and maybe you cannot get that much from this ratio of V stars, just because normally the V star of the tail device is also bigger than the V star of the input device, for many different reasons you may know already. And yeah, so you have some attenuation in the A sense, most probably some attenuation on this part on the V star, but you still have the huge, possibly, differential gain, open loop gain of your amplifier in the gain loop of your common mode feedback. So this means, for instance, of course, then we're not saying really actually how to size CCM, but what is the constraint that actually regulates then these size? Or what is the constraint that regulates how much do we need, let's say, for TCM, right? How big TCM should be, at least a DC, right? So this is a DC but what is the real constraint we should consider, basically? Do you have an idea? How big should we have to go? So potentially here, it looks like it's not too bad, right? We have already in the loop, the gain loop is actually a function of the differential gain, which can potentially be very big. My question is, how do we know how to size it? How do we know how big should we go for TCM? Do you have an idea? What normally regulates? So we have a loop, right? Well, yeah, stability is also an important concern, of course. But then, indeed, so how big it is? What is how much is the DC gain, let's say, of the loop? DC loop gain, right? How it is regulated? Do you remember? What regulates, basically? We want, at the end of the day, we will have a common mode loop. So we will close this loop, right? So we will have a closed loop gain and bandwidth and so on. So how does TCM impact the closed loop gain, right? It's actually impacting the accuracy, right? So basically the closed loop gain accuracy, it's inversely proportional to 1 over TCM. So how much accuracy basically do we need? Then that is the point, right? So I don't know, how much can we tolerate? That's depending on the precise problem that you are solving. But okay, maybe with 1 volt VDD, right, you can kind of accept a common mode disturbance of maybe, I don't know, 10 microvolts. Are there a problem? No, that's not a problem, right? I'm just making up some numbers. Yeah, please. Yeah, the error, exactly. I'm really talking about the static error that you saw also when you discussed settling, and that's inversely proportional, right? It also depends, of course, feedback factor and AV or AV0, right? Something like that. Or actually, it's 1 over T at the end. DC, TCM, DC. So basically, that's it. So 10 microvolt, maybe we can kind of sustain, right? Maybe 1 millivolt even. Well, 100 millivolt, I would say, that starts to be kind of problematic, right? So you don't want wiggles of 100 millivolts at the common mode with the 1 volt, most probably. That depends on your problem or your specs, of course. But so the idea is, even if you are tolerating or you're saying, okay, I want 1 millivolt, let's say, over 1 volt, that's going to be 10 to the minus 3. We are requiring a loop gain of 1,000, right? So this should be kind of 1,000, which is normally possible because sometimes differential gain is already higher than 1,000. So that's even if you assume, okay, a sense of 1, but you can still suffer some attenuation. You can still bear some attenuation with you. So you don't care about really being an amplifier there that is sensing and driving the gate, right, of this transistor. So bottom line, okay, this is a pretty handy topology. Most probably sometimes you are going to use this. But what is the issue with capacitive feedback, right? It's precisely the same problem you had when you discussed capacitive feedback in switch capacitor circuits. So what are we actually sensing here? Are we really sensing the common mode or something else? Basically. Do you remember? So yeah, once you get, let's say, some value, right, some initial value, capacitor can track, right? But the point is, at the really beginning, nobody decided what the V out common mode should have been, right? And so the idea is, normally, capacitive feedback configurations can only track variations in capacitances, right, in a common mode, right? So the initialization problem actually is still there, and we should go and look at that. So that's, let's say, a brute force topology that would allow you to initialize your system, right? So we need to kind of set the output voltage from the very beginning. Yeah?
The second point on the previous slide, large load and what do you do that?
Which second point?
How did you see on large load and
Yeah, so basically, So what I'm so that is if you do CCM large, then the problem is you are loading too much your differential path as well. Yeah. So the loading is high in the sense that you're putting too much capacitance and have on the output.
Right, but it's assuming you're at hyperresistance of DC, it should.
Oh, okay. Yeah, of course. Yeah, sure. So basically, we have said that in this kind of switch capacitor circuit and in integrated circuits, mostly the loading is capacitors, right? So you have input capacitors of the next stage. So in this case, just because of biasing issues, you are also introducing CCM, and that happens to be really at the output. So indeed, for sure, you will have to implement some capacitor at the loading, like you're doing in your project, right? Just because of noise reasons. So you don't want the sample noise to be higher than a certain spec. But indeed, the idea is you don't want to also charge too much, to load too much, right? The differential stage. Okay, so this is, I was saying, a really brute force approach to basically initializing your amplifier at your common mode. So the idea here is I can exploit the fact that normally in switched capacitor circuit, I always have one phase in which I'm not using directly the amplifier, right? So I can call that phase, okay, in this case, the phi samp. And I can use also, the amplifier maybe to fix the common mode problem just right at that time in which I'm not using it for different purposes. So once again, I will have some bias in circuit here, just to make it clear as in the previous slide with some resistor or whatever, and a plug in there. So the idea here is, let's see what happens when one phase is basically on or off the phi samp, right? So I'm assuming here that magically, actually, I can provide the common mode that I want to this circuit, right? And that's the VCM0. Now, how this is going to be done, it's maybe also the topic of, let's say, next lecture, most probably, the references, how to create from the band gap, right? Some stable reference voltages. So let's assume that I have this, right? That magically give me that. So what I'm doing here is actually when, let's say, I close these switches, right? And so I connect that. So in one phase, when phi samp is on, let's say, then basically I'm charging and I'm enforcing, right to both sides of the CCMs, the voltage that I want, the difference that I want. So I would like, indeed, to charge this capacitance to a voltage that is VCM0 minus V bias. That's what I would like. And I can do that when the amplifier is not active, right? Then at this point, I'm basically okay, because when I don't need it, right? So there should be some drift, there can be some drift, but from time to time I always enforce the values of the common mode and the charge that I would like that capacitance to have, right? And so basically, since V bias will always stay a V bias, then even when I'm using the amplifier, then basically I will have the common mode at VCM0, right? So do you see any potential problem with this, what I've called the brute force approach, right? So basically, I have my capacitor, I have my feedback. From time to time, at some phases, I just plug, right, an external magic voltage there, and have my capacitor charged to that difference. And I have my output common mode just set to what I wanted it to be, right? So is that okay? Anything annoying you in this configuration, in this topology? Right. So basically, the point is, I'm really assuming here kind of an ideal, if you want, right? Basically, DC voltage that is provided there. So I'm kind of assuming, okay, that there is magically some DC voltage there. How can I implement that? So can I really have, in reality, DC voltages with zero impedance, right? So that's the point there. So I will need certain way to kind of sink any possible variation in the common mode and in common mode current that there are there. So let's assume indeed that there is a variation, some extra, even small, right, jump in the current, common mode current on both sides. So what am I doing there? If I am in that condition, as soon as these switches get closed, right? So this source, this voltage source, needs to basically sink your current. Now, if there is, let's say, relevant amount of resistance there, you might have some glitches, right? Or you might have some basically movement in the common mode that you didn't want. So you should keep this resistance very small, which implies that most probably you need to spend power for that. Why? Because most probably you will have indeed your band gap or your reference circuit, and it's just not enough to create your VCM0, and so you will need to buffer it, right? And for having low impedance there. And that's going to cost you power. And that's normally some power that you would not like to spend, just because indeed you are spending power to create a small impedance to sink the amount of current without disturbing too much the common mode. But that's only power spent for biasing. It's not power spent for useful operation of the amplifier, right? So you're not going to use it for settling or for something else. So it's normally something that we don't really like, right? On the other side, the other problem, so you will need, to supply this, or to sink, let's say, this extra common mode current that has to flow inside here, right? Plus, you might have, in this case, pretty big glitches, right? Because you are abruptly, immediately going and setting these voltages there. You're not so delicate. So what happens is that if for any reason you had one situation in which VO plus was at this place and VO minus was at this place before resetting the amplifier, right? Before resetting the common mode. And let's assume, for instance, that the common mode was a little bit off for some reasons. Then after that, you will restore it, right? And then you have kind of glitches at the common mode level, so you will have big jumps in a small time, right? So you don't want this kind of behavior. So is there any, let's say, more delicate way of doing this, right? Of performing this? And actually, there is one. I mean, there are plenty, actually, many variations. We will go for the typical one, which also has this advantage, the advantage of providing you possibilities of using the amplifier every time. So most of the time, in switched capacitor circuit, it can also happen, especially when you implement a filter, that you are going to use the amplifier for all the phases, actually. It's doing something good and something useful, both in phase 1, in phi 1 and phi 2, right? But in both phases. So in these cases, actually, this is a little bit, let's say, different. But why? So I basically added another phase. And by the way, so I don't care anymore what this phi amp and phi samp are. These are just two phases there, and they just need to be non-overlapping phases. But the idea is right now, okay, here we've drawn just 1/2 of the amplifier, just because otherwise it becomes too big, the circuit. But you can imagine there is exactly a specular one on the other side. And actually it's basically everything the same as before, apart from these new basically switches, right? And another capacitor that we have added. So CCMS. So what happens? Again, we have our biasing circuit here and the current mirror it's providing your biasing. And now I have an initialization phase that actually uses both phi amp and phi samp, right? So I need to study what happens in both phases. Let's see what happens in phi amp. I have the CCMS here, which is directly connected to the VCM0 and the V-bias. So in this phase, I'm really providing to this capacitor that I added the right spot, right, where it should be, where the amplifier also should be, the common mode of the amplifier. On the other, basically, side of the circuit, then I have basically something similar to what we had before, so the typical the amplifier diagram, and then I have basically my CCM. Now, this is what happens. So I charge and I, let's say, enforce the correct voltage difference onto CCMS. But then, what happens in the phi samp when this switch is active? So I will basically connect in parallel the two capacitances. And still, okay, I will have my tail and device. Okay, so now I have CCMS in parallel with CCM, and they're gonna basically get to the same voltage, right? So now, so why is this working, in your opinion? Why am I still getting what I wanted in the past? So what's happening there between the phase one, let's say, phase one and the phase two, right? So I'm given the desired voltage, the place where to be in phi amp, and then I'm putting this capacitor in parallel with the previous one. So what am I doing? What's happening there? Any idea? So here I have some amount of charge. Exactly, yeah, so that's the name of the game. So basically, depending on the size, I don't know here, now I didn't give you the size of this capacitance, but basically, so what happened is that if I assume that I wanted some like 200 millivolts there of difference, right, from the beginning, and here, because of fluctuation in the common mode, I just had 100 millivolts. So what's going to happen at the end? Well, where will the final voltage difference settle? I don't know exactly which value, but what is the range, right? If I said, okay, I start 200 millivolts from one side, 100 millivolts on the other, so they will share the charge, right? So I will sit in a spot like where? Something, what is the range? In between 100 millivolts and 200 millivolts, right? So that means that basically, gradually, in a, let's say, graceful way, right? I'm getting there, but I need some time, but I'm still transferring charge, right, from, let's say, my, if you want, reference source to the amplifier. And at the end of the day, I will settle to the common mode that I want, right? So the idea is it's going to converge because there is no other way of imposing, you see, onto this capacitance, onto the CCM. There is basically no other way of imposing the common mode. That's the only way, right? So there might be some disturbances, but these disturbances will be kind of the current, right, in this case. Let's assume that I have also some disturbance here, as I was saying. So this current will be, of course, also transferred to the CCMS. And in the new phi amp will be sucked by, again, the voltage, right? Voltage source that I have, VCM0. So I will have, of course, on both sides, some transfer of charge. So potentially, if I don't have big, huge disturbances at the common mode, I will soon converge, after some time, converge to the value I want. On the other side, if I have some disturbances, these are kind of recovered, although, I mean, not really immediately, but with much less power consumption in this case by the VCMO. So of course, in order to kind of sustain this delta I need some constraints, let's say, on the impedance, right, that the common mode control is seeing there. So does this capacitor with switches at the edges tells you anything? Have you ever heard about basically switched capacitor resistors? In the past. Who heard about that? Okay, yeah, a few people. So basically, that's what I basically implemented here. So I just used switch capacitor technology to implement just a kind of resistor, which while resistor is just transferring charge continuously, right? Because there is a continuous flow of current over there. Here, I'm transferring charge from one spot to another spot in packets, right? In small quantities of charge. But at the end of the day, if I look at the end of the cycles, I've had some charge transfer. So all that I need to do in order to kind of absorb, let's say, this delta I need to enforce that this equivalent resistor that I'm seeing there is small enough, right? Like this is similar constraint as the one that I had on the previous circuit, but it's much more relaxed. And you will see this when we'll discuss also capacitance resistance and so on. So basically, switched capacitor resistances. So here, actually, the resistance is determined by both the CCMS and also the clock frequency. But okay, so we don't go through this in too much detail. But that's it. So I have a switched cap R, and I need this to be low enough, right, to sustain delta I. So any disturbance here, I have to handle anyway these disturbances on the common mode. But this is a much softer, right, technique, and I'm not requiring anything on the phases, right? Of course, yeah. So that concludes basically this series. So that's why it is called continuous common mode feedback, because I can use the amplifier continuously. Yeah. Well, because now I expect much softer jumps since I'm transferring. So if I do basically the CCMS, right, small enough, so I will always transfer small amounts of packets of charge, and that's why it's softer basically. So I'm saying I'm not abruptly bringing that voltage to the desired spot in a very short time. I'm doing it gradually with time, and so if I'm transferring a small amount of charge of a small amount of the same current, now I don't have that requirement. I don't have a big jump, and so I don't need any more, a very, very small. Still, I need a small resistance, of course, a small resistor, but I'm not anymore, I don't need anymore that buffer, right, that would bring me basically huge power consumption. I can implement kind of small switch cap resistor because I can play with frequency and with the value of the cap, while at the other time I was just obliged to use some buffering with a very small RO. So on the other side here, the glitches are much smaller because indeed I'm just saying, okay, it will take more time, but I will do this softly, right? And okay, so let's go then to the other topic of the day. Of course, anyway, you will have to, even if for the common mode feedback, right? Everything that was analyzed and we talked about for any possible feedback also applies to common mode feedback. So even for common mode feedback, you may want to basically, oops, no, it's not actually the one. You may want to also check the stability of the loop. And possibly run also a transient analysis to see if when you basically have a step in VDD, right, you can still guarantee your stability. So not only the phase margin is important there, but also some transient. So this, everything that we said, sorry for this. Oops. This is a pretty old tablet. Needs some time. Mm-hmm. Okay, sorry for that. So, as we were saying, multi-stage amplifiers. So my question is, why do we need a multi-stage amplifier in the first place? Right. So most probably you already have seen some stuff here from 140 and from your undergrad. So what is the problem with just single-stage amplifier? So one of the issues is indeed that you trade gain with swing, right, in this amplifier. So if you just consider our single stage amplifier, then basically assume that you want a certain swing, right? The point is, swing is normally eating your gain, right? So what happens is, okay, let's draw it to clarify. We have a PMOS, for instance, current mirror there with some biasing, and then you have your common source stages, right, as we have seen many times so far. So the idea is every time you want some swing at the output, you end up with pushing these basically transistors, both of them or the current source, far from saturation, right? Where your arrow most probably will be degraded. So your gain will be degraded. And even if you have different solutions for that, like cascoding, like if you want to use a cascode, well, that's still basically hitting your swing, right? So you will get some gain, but your swing is most probably impaired. So the idea is sometimes you don't want to do that, especially with low voltages. You need both high gain and high swing. So that's one way, right, of doing that, using a multi-stage amplifier. And actually, you can say that even the gain-boosted cascode that was kind of not impacting too much the swing and at the same time giving you a lot of gain, or much more gain, is kind of a multi-stage amplifier disguised, right, into an inner loop. But so the idea is that if you just decouple basically these trade-offs, then you can have an amplifier A1 with amplification A1 and then another with gain A2. Right, on this you can go with very high swing because maybe you don't need that much of a gain there, while on the first stage actually that's your gain constraint would be placed, and you don't need actually to talk about high swing here because you will be increasing that swing with the second stage. So that's actually one way, right, one of the advantages, because on the other side you might have many different disadvantages, like power consumption might grow, right? It depends on the spec, of course, you are going to implement. But one of the biggest challenges with multi-stage amplifier is certainly stability. Why? Because you will end up with a bunch of poles, right, in your loop gain, and so at the end of the day, you need to take care about these poles. Yeah.
Well, even if say you're operating in like a pretty much open loop situation, are you gonna also have potentially more delay if you have the multi-stage iteration?
It depends on the sizing, of course, where you place the poles and the zeros, but yeah, ideally could be like you're slowing down the chain, right, or even if you're. But that depends. Of course, if you put more power there, then you can kind of compensate this eventual delay that you get. And so, yeah, that's also and depending on how much gain do you have. So if you spend power in the gain bandwidth of the two stages, how much gain do you need? So if you can trade gain for bandwidth, then you can still go faster. But indeed, so those things have to be seen, let's say, case by case, on a case-by-case basis. But indeed, the stability is a big problem, a big issue, because indeed you get a lot of poles, as we were saying, right? And so just to warm up, right, let's go for the simple case that we know already. So true common source, the very simplest case, in the sense that you analyzed already this in the past. And let's assume, for instance, that since I have here a common source that might be ideal, and so I will just place some output impedance here, R1, to model the output impedance, and then an output impedance R2 for the second stage as well. So yeah, warm up. Where is the first pole located? If this is the situation, P1, most probably. Minus? Yeah. So, okay. It's minus 1 over R1C1. And similarly, the second pole will be placed at this frequency, or this omega, right? So, generalized frequency, actually. So let's assume now that I've just placed these two poles really closed spaced, right? So basically at the same spot. Let's assume they are just piled one on top of the other. Now, my question is, and let's assume that we are tying this amplifier in feedback as well. My question is the circuit, when I tie it in feedback, stable or not? generally. What do you think? You mean which gain? The loop gain. Yeah, exactly. So basically, first of all, let's go more deeply into that. First of all, this is a kind of tricky question, right? Because actually, I didn't give you any information about the feedback, right? So I might have potentially some poles and zeros also into the feedback network. I might have some gain into the feedback network. So I don't know actually what's going on here. But okay, let's then be more precise, right? Let's then assume that I have even unity gain feedback. Like I would have minus half, that could be minus 1. Most of the time, people, when you consider only passive networks, the unity gain feedback is considered to be the most pessimistic situation. But you might have some gain also in the feedback, right? And so that is even worse. So let's assume that I'm tied, just connecting them, let's say, in a unity gain configuration. Then my point is, okay, so let's even plot, right? What is the body plot of the loop gain? So the magnitude of the TS, T of S, over as a function of omega. So I would have something like that. So I'm assuming that the two poles are at the same spot, and I'm having minus 40 dB per decade. And what about the angle, the phase plot? So the angle of T of S. So I would also have basically a phase shift of minus 90, right, at the true poles, where the true poles are, and then something like that, right? And asymptotically, I would reach basically here's minus 180 degrees, right? So here we are now. Now I guess we have all the mathematic tools to reason about this system. So we are in unity gain feedback. So my question is again, is this now stable or not? I guess I'm asking really the mathematic question, right?
Technically it is, it's an endless pass.
Right. So basically, theoretically, but very, very, really, really theoretically, right? You will always have a positive phase margin here, right? You never hit minus 180. So mathematically speaking, this shouldn't, if this is the real model, right? If this is the reality, that should not oscillate, right? So it's kind of stable, right? Should be stable. But that's actually the tricky question. So the point is, does this really, do you really trust this on chip, right? So does this really hold? No. Why? Give me an example of what could go wrong here. So basically, I have some connection, right, between the two stages even. I have one point here and one point B. So I have to kind of some metal there, right? Could be whatever. Could be 1 micron. Could be even 10 nanometer long something. But anyway, I have to go from one spot to another spot, right? And I cannot travel faster than the light speed or something like that. So I will need some delay there. There is a phase shift, right? I will have a phase shift just there. So I will have some resistance and then potentially also other capacitors and so on, parasitic capacitances in the metal layers and so on. So just because there are these things, and then potentially even in the amplifiers, because most probably the amplifiers have a bunch of transistors, not only this one that I have drawn here. So you will have additional poles and additional phase shift also in the loop. So the idea is, okay, 1 degree or 2 degrees of phase margin, they're not reliable, right? They're not robust at all, right? And even if it was stable, so could I just be happy about that? So it might happen with a very small phase shift, like in the phase margin, let's say. My settling behavior would be not the one that I desire, right? So, for instance, assume that you have a very small phase margin and you have basically a step, then what kind of behavior would you expect for the amplifier with a small phase margin, right? So it doesn't oscillate, most probably, because mathematically we still have a good phase margin. It doesn't oscillate, but it settles very slowly, right? And it could kind of ring before really getting and I could have even a bigger oscillation there. So the settling will be pretty slow. I will get the value that I want after a long time. So I might not be happy at all about an amplifier like that, right? So just also because of what we have already seen, like the settling time and the settling issues. So let's then go and a little bit review how to make it stable. So the point is how to recover, right, the phase margin that we want. So let's assume right now that we were not so mean like we were in the previous slide, which we placed the two poles just at the same spot. Now we place them a little bit different position, and we still draw the magnitude and phase of the loop gain, right? And so I would have something like that. If I place one pole here, P1, and then P2 here, then I would have something like 20 dB per decade up to P2, and then I will go with 40 dB per decade. And then I will have my crossover frequency here, or omega there. And on the phase plot, basically, we will have the angle, again, of T of S. At this point, phase plot wouldn't be so steep as in the past. I will have here just 45 degrees, minus 45 degrees phase shift. And then we'll get to 90. Then the second pole will start kicking in, and then we will have minus 135 here. So this is minus 90. And 35, and then again minus 180, right? So this is more or less what would happen if I have a little bit the poles spaced in between them, some space in between them. So now let's assume that I want actually to recover my phase margin that I was losing or was missing in the previous slide, right? So basically what I should do, right? So just what you should do if I would like 45 degrees phase margin. Actually, in this configuration. If I'm assuming that this is the gain of the loop gain, what should I do? What condition should hold there? Yeah, so basically, where should indeed the crossover frequency be, right? It should be right at. Yeah. Okay. The crossover frequency is okay. Right at. So the crossover frequency is this point, right? So I should put the crossover frequency placed at the spot of the second pole. So this is basically equivalent. Either I should lower, right, the gain, or I can basically just increase, draw another axe here. But I mean, the bottom line is I'm reducing the gain, right? So basically, to get this configuration, I needed to reduce the gain in the loop. So. And there I would have 45 degrees. And actually, if I want a little bit better phase margin, then I should even go farther with this omega axis translation, right? I should translate it even higher, at a higher position. And this impacts my gain. So it looks like basically T of S, the amplitude, the magnitude of T of S should be very small if I really want to kind of stabilize or have my phase margin just with these techniques, right? Yeah, right. Yeah, indeed. So basically, that's the name of the game. So you got it, basically. That I don't want to compromise my gain just for getting a phase margin, right? Because at this point, if I consider, for instance, this configuration, like for the 45 degrees, basically what I'm saying here is that the gain that I can allow for 45 degrees is just the ratio between the two poles, right? So you can compute that. And so that means that I'm totally linking my gain to the distance of the poles, which is something that I wouldn't like, right? So I want to decouple this stuff because, I mean, how far can the poles be? Like, I don't know, 10 times, one 10 times than the other or something like that. And then I would have at most a gain of 10, right, in this. So, but this is not the case, right, because my accuracy, static accuracy in the closed loop amplifier requires me maybe 1000 or something more, like for the gain. So at the end of the day, actually, I should go for smarter ways of gaining phase margin. And that's basically what you learned. We talked about pole splitting right now. Rachel was mentioning pole splitting. That's the Miller compensation, right? But the whole point is here compensation. So you already saw some of these techniques. Actually, we assume that you know many of them. We just want to recapitulate or recap a little bit some of them, right? The basic categories of compensation that you have. And one of these is narrow banding, right? So before even going to pole splitting, that is the smartest, actually, compensation techniques that you can, I just want to remind you a little bit these other couple of techniques, narrow banding and preamp, using a preamp also. So narrow banding consists in this, basically. If I, at the beginning, had my initial TS, right, with two poles, P1 and P2, as I've drawn also before. The idea is I want to lower the first pole as much as possible to get the gain as I want while still having a good phase margin. So either I add another pole or I just shift the first pole as much as possible so that I already have my 20 dB per decade. So my pole now shifts here, 20 dB per decade roll off, and then I would hit the omega axis much before than much earlier than before, and then actually, okay, I will start with my minus 40 degree later. So the point is, there I'm going to be stable and I'm going to have the phase margin that I wanted, right? But at what cost, right? So let me draw a little bit better. Okay, so what is the cost here? I basically made my amplifier slower, right? So the bandwidth in closed loop, which is linked to the unity gain bandwidth in this configuration, is actually much smaller than I had before. So, by the way, this is something that sometimes I would like, and that is applied in some configuration when I, for instance, want to do some offset cancellation. In some system, offset is so big, or maybe I want to save power and to have an efficient design, and so I would like to cancel the offset because otherwise that disturbs my signal. The signal might be maybe too small as well. So I might use this technique, narrow banding, so basically deciding to narrow down my band, to restrict and to decrease my bandwidth, just for the purpose of cancelling the offset. Like, for instance, I could have a system like that, right, in which I have an amplifier, and I'm concerned about the offset that this amplifier is placing at the input, the V off, of this A1, right? So I might architect a feedback in which I even place an active component in the feedback network. So let's assume this is basically a low-pass filter with a very small pole, FP, and basically I have a negative feedback here. I connect it in negative feedback with the source, with the input. And that is one system, for instance, that in which I'm using narrow banding, in the sense that if you break the loop and you consider the loop gain, I'm placing, now the orientation here is like that, right? I'm placing basically a very small pole there because I want to not to compromise the gain. I need gain, actually I need a huge gain, both in A1 and in A2, right? And basically, this allows me to kind of cancel the offset. So here is the question now. If I want to, if this is V out and this is V in, what kind of transfer function, for instance, this would give me? Like having the loop, a low-pass filter, and I want to compute the magnitude of this transfer function. How does it look like, in your opinion? So this is a kind of low-pass filter also, right? A1 would be a low-pass transfer function. I have a low-pass transfer function in the feedback path with a very small pole. What do I get, in your opinion? as a result. How does it look like? So I want to cancel the offset. Any clue? I would any idea? So let's a little bit elaborate more on this. So if I want to actually compute V out over V in, right, more or less would be A1 over 1 plus A1, A2, right? So basically, if A1 and A2 are, have a bigger gain, right? So you can approximate this transfer function. It's approximately 1 over A2, right? So what does it mean? So whatever pole I had in A2, I find it as a 0, right, of the system, right? So basically, if I had the very low frequency pole, I will have a low frequency 0 now in the loop. So basically, the transfer function will be right now basically a bandpass transfer function, right? So something like that. And whatever pole I had in the loop, it's easy. You can go and do more calculation on that. Whatever pole you have in the loop, you actually right now becomes at 0. And so if you really wanted to cancel, right, potentially, so what you want to do here is actually you are really happy about a very low frequency pole because you don't want to damage your signal, right? You don't want to cancel your signal. You just want to cancel the DC component, your offset. So potentially, actually, you would be happy to, I mean, how much gain, for instance, if you could, right? How much gain would you allow in the path? Like, okay, you could have here, I don't know, 100. Here you could potentially have, I don't know, 1,000. But, okay, so how much, right? If you could push it as much as you can, you would go for, basically, since you want to basically null the DC component, right? Any idea? So you want 1 over A2 to be almost 0 at DC. Right? So you're really looking potentially for a component that has infinite gain, right, at AC. So an integrator, for instance. Yeah.
Is that V out over V that's at DC on the right there?
The expression, you mean? Yeah, the expression, okay, I mean, even if A1 and A2 are a function of S, you can still write it. But okay, you can assume, for instance, a DC also reason about that. And so basically what you notice here is that indeed, if A2 was infinite at 0 frequency, right, I would have a complete nulling of the offset. So potentially an integrator would do the job, right? And if it could be possible to have ideal integrators. So, but let's go now and look at a dual of this technique. So in the first technique, what I did is basically I placed the first pole as close as possible to the origin or as small as possible, right? While here, I'm actually saying, okay, let's place the second pole as far away as possible from the, let's say, so that I cannot disturb from the crossover frequency, right? And that's the preamp technique. So if I had an amplifier with a certain transfer function, which is again maybe just a one-pole transfer function, and that's my A, right? So the idea is I can boost a little bit the gain of this while still having good phase margin by using some preamplifier. So I can still boost a little bit the gain, but I need to take care that the second pole that I introduce is far away from the crossover frequency, so that most probably I will not perturb the crossover frequency too much, right? And then I will have the second pole that starts far away, and so I still have a good phase margin. So I overlap, I add another preamplifier, and this is a kind of way of taking care that the chain is still stable, right? There will be when in closed loop. So what is the limitation of that, right? I can use this technique if I'm really shooting for very small additional gains, like a factor of 2 to maybe 10, right? or maybe since I'm talking here about an implementation, you see, I precisely decide to have here a resistive load, because if I had just the arrow of the transistor there, I would have huge gain normally, and possibly I could not place really the pole very far from the pole of the second stage, right? So to really have this boost in bandwidth and just a little bit of a boosting gain, I most probably need to go to an implementation where I use a resistor as a loading, right? So it's a resistively loaded amplifier. That's normally typical preamplifier configuration used. And so I can get indeed a boost of gain even smaller than 10, right? 2 to 4 or something. So it's good if you need just this small boosting, right? But I mean, you cannot really use this technique everywhere, because I mean the advantages that you get, there are not so many. And by the way, okay, of course, nothing changes if you use this as a post amplifier, right? So I called it a preamp, just because indeed sometimes the purpose is to get some to adapt basically the input swing to the swing of the second amplifier, and so you might preamp the input signal. But even if you use this as a post amp, right, doesn't change. So you still have two stages, and one really giving you a small gain and a high bandwidth, right? But still, let's say, making the whole chain stable. And so, basically, if this is the situation, so we've seen narrow banding, we'll see the preamp technique, but as already we mentioned, basically the smartest things to be done is actually what is called Miller compensation. That's actually the clever technique named after Miller, of course, that introduced it. And so as I see, as you see here in this basically two stages, what I've done is I've placed the capacitor, one capacitor, the compensation capacitor, like CC, in between these two nodes of the second stage, the input and the output of the second stage in feedback. That's a negative feedback as well in the open loop amplifier, right? So why is this working? Why is so it's very common form. It's called pole splitting, right? So what is nice? What is a nice technique? Do you remember? What is what are the benefits, right, of these techniques? Exactly. So basically, it's getting both the two advantages that we got with the narrow banding and with the preamp technique. So we are pushing at the same time the P1 at lower frequencies, like we were doing in narrow banding, and we are pushing P2 to higher frequencies at the same time. Does anybody remember why this happens physically? What's going on there? How is it that I'm getting this result, right? Do you remember what was there is basically an effect that has the same name of the right, but indeed, so this kind of Miller effect, right? Miller capacitance. So it's like the CC is seen as something like AV times CC. So that's the kind of Miller effect. But okay, we're not explaining this still physically. We remember from why this happen. It's really that CC gets multiplied, or it's physically AV times CC. So why this happens? What's going on there? Yeah, exactly. It's basically on this line. So it's the name of the game here is the level of voltages that you have on both sides of the capacitance, right, of the capacitor. So most probably here you will get after, like if we assume just 1 millivolt, right, signal swing there, most probably if this stage is giving you a gain of 10, then you would have a minus 10 because it's an inverting stage. And in this calculation, I'm just estimating without considering the feedback cap, right, there. So minus 10 millivolts. So the bottom line is the capacitance has at the terminals like a difference, which is 1 plus AV times the V in. So if this was the V in, of the one terminal of your capacitance, it's actually what I'm seeing, where AV is actually the gain of the second stage. So GM true RO, right? True if you want. So that's what's happening here. So it's just physically, it's really the amount of charge that is transferred. And because I've placed this capacitance between two spots through which I have a huge gain, right? A potentially high gain. And so, well, we have explained now why the dominant pole goes to lower frequencies, because indeed the CC gets basically translated at the input, right, like amplified by AV. And so there is a dominant pole, let's say, that gets shifted to lower frequencies. What's the story with the high frequency pole? Why I shift it to higher frequencies? Do you have any clue on that? What's going on? So do you remember where was the spot of the second pole, right, at the very beginning? So it was -1 C2 R2, right, 1 over C2 R2. What's going on here? Why I shifted to higher frequency? Any hint? Any thought? So what's happening at high frequency? At high frequency, I can assume that the first pole has already basically done his job, right? So what can I assume on this configuration, on this circuit? That CC is kind of grounded or shorted, right? The terminal of CC. So actually my amplifier now looks like that, right? First stage, and then I have the second stage with some cap, and diode connection. So what happened, right? So the resistor that this capacitance C2 is seeing is not anymore RO. So at high frequency, it's basically 1 over GM. And that's the idea here. We basically pushed also the second pole at much higher frequency. So we are getting, by just placing the capacitance there in that spot, we're getting two advantages, right, at the same time. So indeed, then I really would like to compute an exact expression, let's say an approximate, but much better than the one that we got before, of the poles. So let's redraw then the amplifier so that we can have a reasonable expression for those. So I have the first stage, and then R1, and then basically CC, R2, and C2. So here I am. Let's basically find an approximate expression for P1. P1 is more or less given by -1, as I was saying, the resistor R1 and the capacitor that this resistor sees. So this capacitance is going to be CC times 1 plus AV, but we have said the AV is the AV of the second stage, so GM2 R2. So let's notice that here, since I'm assuming that CC times AV is much bigger than C1, I didn't even bother to draw the original C1, right? So it's already an approximate expression. Otherwise, you should include C1 as well. But then I can still go farther with approximation and drop this 1, right? Because I assume that GM2R2 is even bigger. And I can drop this 1. And what I can do also is I multiply both the numerator and the denominator by GM1. So I will get GM1, so the gain of the first stage. And we will see in a while why I'm doing that. And GM1 here. R1. And then I have GM2 R2 CC. So the nice thing here is that now I've isolated the DC gain. GM1 R1, GM2 R2 is the DC gain. So I can really write everything like minus GM1 over AV0 of the whole chain times CC. So this expression gives me basically almost immediately, right, what happens if I tie this amplifier, because I know this is the dominant pole, and it tells me if I tie this amplifier in a loop, what happens? What would be the bandwidth, right? What would be the bandwidth if I would say I have an F loop factor, loop gain of, let's say, in the feedback gain of F? What would be, for instance, the new bandwidth of the system in closed loop? Why this expression is pretty handy. Yeah, so times F, right? Because I would multiply by the AV0. So I would need F times the gain times the bandwidth. So it immediately gives me the basically the loop gain. But we will get back to this afterwards, just to motivate why I manipulated the expression in this way, right? So, and what about the second pole then?
That's the expression there is the.
Yeah, basically this is the omega the crossover frequency. Basically omega t, omega crossover of the loop gain. So it's basically F, the feedback gain, times the gain bandwidth, right, of the open loop amplifier. And that's why, so the gain is now at the denominator, so it's immediate to see it's actually proportional to GM1 over CC. And then, actually, I have P true. Basically, I have P true. And P true, as we were saying, since I can assume that CC is shorted, so it's really minus GM true over C true as an expression. Now, did I end the story here with the singularities of this? Look at the circuit. So do I have just these two poles and I'm done, or there is some other singularity there? Do you see any other singularity? Well, there is, okay, yeah, this is the R2, but R2 is kind of in parallel with 1 over GM. But what is, so I have this capacitance bridging the input and the output of the second stage, right? What is this capacitance giving me also?
Zero.
Basically, it's given at 0, right? Because I have a kind of, in the feedback, right? I have a feed forward in the local feedback of the capacitance. I have a feed forward path, right? And so this is causing me at 0. And can you infer just a little bit what could be the sign of this 0? Do you have any hint on which side of the complex plane? It's in the right-hand side or left-hand side of the complex plane? It's positive 0 or negative 0? How do you very quickly see this? How can you see this? If it's a positive 0, if it's a negative 0?
If it's a positive 0, there should be a frequency where you have a gain of 0.
Well, not really, because normally, okay, we're reasoning here actually in the S domain, right? There should be, of course, an S domain frequency, let's say, which you have at 0. But actually, it's really the sign of the gain before the 0 and after the 0 that counts, right? If there is a 0 with negative sign or with positive sign, that shifts the direction, the amplification. So before, basically, that capacitance is activated, or let's say acts, like, so you have an inverting stage. So we would have just a common source, right? If the capacitance is open. The gain is basically for an input variation like that, I would get an output variation like that. After, what does happen? After I have something like that, I have a diode connected transistor, right? And so whatever I get here, it's just a wire, right? It goes to the output. So I shifted the phase. I shifted the sign of the gain. So that is a very quick way to see that actually there was a negative, there is actually a positive 0, right? It's in the right half plane. So can we quickly find the frequency of the 0? Where is located? Do you remember the technique I think you applied it also in when you talked about settling time. So what should we do? We should kind of impose, right, that the output is basically 0, right? And find out, so the easy way to see that, you kind of ground the output, that's 0, and then you want that all the current that flows into the capacitance is the one provided by the GM, right? So you end up with something like V1 GM2 equal to S CC VI, and so finally you get the S0 as being GM2 over CC. So this is actually the expression of at 0. Now, question is, so we thought that we solved the problem, right? We have now a stable, maybe most probably with this technique, most probably stable amplifier. But how is positive 0 for the purpose of stabilizing an amplifier? Is that maybe good thing? Is that a bad thing? Or possibly a very, very bad thing? What's your guess? Having a positive 0. Are we okay now? Are we happy? Let's leave it there. Yeah, that I guess then will come afterwards next time. But actually, it's very bad, and you know why? Because actually, it's a true, really bad effects, right? So on the gain side, it's actually pushing the crossover frequency far, right? Because you have something like that. You have at 0, so an increasing gain. And on the phase side, is actually giving you some more negative phase shift. So you see so what happens. So you go minus 90 degrees phase shift after the 0, while still you don't have the crossover there. And so I guess then we can go last few minutes to discuss actually what is actually really needed here at this point, now that we have all the complete configuration. What we are going to do is actually really some phase margin engineering, right? So it's not that, as you were taught maybe in 140s, you have to just make sure that your amplifier is unity gain stable. It's not just what we want, because it depends on the feedback. Most probably, in your environment, you know everything that you have to deal with. So basically, you have some settling requirements, most probably. So these ones are going to dictate really how much do you have to compensate your amplifier and how far you have to go with your phase margin, right? So, and that's actually a bunch of expressions that help you understanding how to actually engineer really this phase margin. And we walk through these slides and then we conclude for today. And so basically the whole idea is, as we were writing already, all the expression actually we already had from previous calculation. This is the basically crossover frequency of your loop gain. And then one thing that you want is actually you want to push the second pole at a factor of k times the crossover frequency. That's normally the problem of getting the phase margin that you want or stabilizing your amplifier. Well, you know, for instance, if you want 0.1 % settling accuracy, then maybe this K factor, it's a kind of a 3.3, right? Or something like that. So based on settling and based on the behavior that you want, then you decide this K factor. And that's where the second pole actually should be placed. But then, indeed, basically, what this tells you, actually, if you then figure out, if you just replace the expression that we have for the second pole and the expression that we have for the omega u, then you get this basically key expression that allows you to understand how CC should be made, right? And so what tells you is that the higher K you are choosing, right, the higher phase margin you are going for, then the higher the CC that you need, and most probably the higher power also that you might spend. But not only this is also, if you have a higher F, like your feedback, the higher gain in the feedback network, that's also called for an higher CC. It's calls for an higher CC. On the other side, what is the impact of C2? If you also need to drive an higher C2, then most probably your CC is going to be higher as well. And for a fixed CC, larger C2 are lower in the phase margin on the other side. So to keep the same phase margin, you have to increase CC. Otherwise, if you fix this, your phase margin lowers. And this is normally very different than OTA single stage, right? Because in single stage of TA, the more you loaded the OTA, the more stable you were, right? Because the dominant pole is at the output. Here, the dominant pole is at the, say, input stage, the Miller stage. And so the more you load, the worse the phase margin becomes. So it's just an opposite behavior as all the amplifiers that we've seen right now. And then, of course, there is the phase lag due to the zero that, as you indeed already mentioned, you want to kind of avoid, and you already know how to do it. Because as you can see, you cannot make this zero very far away from the omega u. That would imply GM2 much bigger than GM1. But having GM2 much bigger than GM1 is harmful, right? Because notice that GM2 is not giving anything about good about your bandwidth, right? Omega u is only depending on GM1. Omega u. So GM2 is actually the second stage GM. It's just power that you are most probably, just to make that zero far, to place the zero far away. If you go for GM2 larger than, much larger than GM1, you're just wasting power. So it's something that you wouldn't like to, because you're not employing power for good settling. And so indeed, that's nothing that you can do. There's almost nothing that you can do. The position between the zero and the second pole is decided by basically this true cap ratio. There is not that much you can do to cancel that, unless, as you were saying, you were actually trying to null or to the zero with the resistor. And we conclude here, and I guess basically the technique is indeed to put in series with the capacitance a nulling resistor and try to place the zero as far away as possible. But you will pick with LUD from here and continue.